Let's take a look at a method called Euler's step-by-step method. And this is sort of falls under the category of numerical methods. So we're going to approximate a solution. Before we start the method, let's just look at this sort of quick example. Okay. So imagine if you were given like a differential equation, dy by dx equals 3x squared. And you knew some information about, like, we don't know what the original function is. We know that the derivative is this, but we know some information that, like, when x equals 1 on y equals 2 on the original curve. And then if we were asked this question, like, well, if we know what the differential equation is and we know a point on the original curve, figure out when x equals 1.1, like another x value, what would that y value be? Okay, now obviously for this question, if you got asked this, you could literally just integrate, solve this differential equation, and you'd end up with y equals x cubed plus c. You know the point on the curve, so you can sub in, and we get y equals x cubed plus 1. Now clearly when you've got the original function, you can then answer this question. So if x equals 1.1, we want to figure out what the y value is. Once you've got the original function, sub in 1.1, and we get the corresponding y value of 2.331, which is fine. But this topic is not about finding the exact solution, and it's definitely not about integrating to solve the differential equation. What we're going to look at is some sort of differential equation which is too complicated to solve. Like, we don't want to integrate it, we don't want to solve it. Like, say for example, if we had dy by dx was equal to sine of x cubed ln of root x. You know, if you had some mad differential equation, now we can't just integrate this and solve, but we can still, if we don't know what this original function is, but if we know a point on the function, we can approximate what the next y value would be. Okay, and that's what this technique is. It's essentially about, you've got a differential equation, you've got a point that you know was on the curve, you don't know what the original curve is, we can't integrate it to figure this out, but we can still approximate where the curve goes, given a point and a derivative. Okay, you may be asked to show where this comes from, so I'm going to quickly show you where this formula comes from. So the notation we use is xn, yn. So assume we've got a coordinate on our curve, and what we're trying to do is we're trying to approximate this next xn plus 1, yn plus 1, this next point along the curve. Now the way that we do it is we approximate this point by, because we know what the gradient is, remember we do know what the gradient is, if we think about the tangent at the point that we know, that point there that we're trying to find, we actually end up approximating it as that point on our tangent. Because if we know the original point on the curve and we know the gradient, if we draw a tangent at that point, that there is going to be our approximation to that actual value. So if we think about this triangle, that gradient there, remember it's just the change in y over the change in x. So we could say that yn plus 1 minus yn divided by the change in x. Now we could write xn plus 1 minus xn, but don't forget, like in numerical methods, that small increase, remember I'm drawing this quite large, but this would really be only a very small increase. If we had like a small step, we'd be able to relatively accurately approximate where this curve was going. That increase in x values we call h. Okay, h, remember, you've seen that in quite a few topics now. It's like a small increase in x, we denote as the letter h. So that difference there would be h. So the gradient of our tangent we know is dy by dx. Okay. But we also know dy by dx is this function, wherever the function is in the question. So we could write yn plus 1 minus yn over h would equal to this function of x. And if we rearrange this, remember, don't lose sight of what we're trying to do on this question. We're trying to approximate, like, if we know an original point and we know our derivative, we're just trying to figure out where does the curve go, like what's our next y value. This is the thing that we're trying to figure out. So if we rearrange this formula, we end up with an iterative process. Sorry, that one small mistake. We evaluate the derivative there, that gradient would be the derivative at that x value, so I should be writing the gradient evaluated at xn. Because if you sub in that x coordinates, you get that gradient, don't you? So that is our formula that we can use for this step-by-step approach to approximate where the curve goes. Sometimes the function won't just be a function of x, it might be a function of x and y. So you might get some differential equations with x's and y's in, and in which case the proof's exactly the same. You know, the gradient is a function, this gradient of this tangent here is a function of x and y. So we just follow the same process, changing y over changing x. The gradient's a function of x and y, and then the answer we end up with. Would also be very similarly written like this. Okay, I don't think it's going to be asked, but it does say on our spec that like we need to see where this geometrical proof of this comes from. So it could come up. You definitely want to highlight this in your notes. Okay, so let's try a couple of examples that sort of use this formula to approximate our next y value on our curve. Okay, example 1. We're given a differential equation. Dy by dx equals 1 over 3 minus x. We know a point on the curve, which is our initial x and y value. We're asked to use a step-by-step method, which is Euler's step-by-step method. We do get this in the formula booklet as well, I should say that. Step of length 0.2. So essentially what this is telling us here, h, or our increase in x, is 0.2. And we need to go up to 1.4. So the way I would start to set this out is to just be clear on your notation, like what's x0, what's y0, what's x1, what's y1, and if you think about it, so far we know that our initial x value is 1, our initial y value is 4. We're going up in 0.2s, so the next x value would be 1.2. Now we're asked to figure out what y is when x equals 1.4, so we're going to have to actually use this iterative process twice, because we want to end up with, like, that's the thing that we're being asked for. When x equals 1.4, what does y equal? Okay, so using the process, we could say, well, y1 would equal y0 plus h times f of x0. So y0 is 4, h is 0.2. And then we evaluate the function. Don't forget the function is the derivative in this question. Okay, if you look on the formula booklet, it refers to like f of x equal to dy by dx. So this function is our derivative that we're using. We're not going to integrate it to find the original function, like, because we're approximating the solution. Okay, so we're subbing in to our derivative, our x value, x0, which is 1. So y1 would equal 4 plus 0.2 times 1 over 3 minus 1, 1 over 2, so divided by half, no, times by half. And we get 4.1. So we know that y1 is equal to 4.1. Remember, we're aiming to end up with, when x equals 1 and 1.4, what does y equal? So we need y2. And just think about the notation, be careful. y2 would equal y1 plus h times f of x1. So y2 would equal y1, which is 4.1, plus h, which is 0.2. And then we're going to evaluate the function at x1. Okay, so it would be 1 over 3 minus x1, which is 1.2. So we get 4.1 plus 0.2 times, 1 divided by 3 minus 1.2. You can type that in, obviously it's going to be 1.8, 3 minus 1.2. Close the bracket. And I'm getting 4.21. 3 decimal places. Okay, so maybe show a few more. 4.21111, so therefore y2 is equal to 4.211. Okay. Just out of interest, it does actually say in this question how accurate was this approximation. Like just for this first one, I've given us a differential equation that we can actually solve, just to see if this technique was accurate, because we can be asked about like whether the solution's accurate or how to improve the accuracy. So let's think about this differential equation for a second and see if we solve it, what we would end up with, and if this approximation is going to be close. So if we've got dy by dx equals 1 over 3 minus x, separate the variables and integrate both sides. Remember, dy we're integrating 1. For this one, we're integrating a fraction. So I'm thinking f dash over f. Look at the bottom, the derivative is minus 1. So just make it minus 1 by putting a minus outside. So we would end up with y equals minus ln modulus 3 minus x plus a constant. Figure out what a constant is. So we know that when x equals 1, y equals 4. So that'd be ln2, so minus ln, so 4 plus ln2 would equal our constant. So the function we've got is y equals minus ln modulus 3 minus x plus 4 plus ln2. I could group the logs together, but really all I really care about is once I've integrated and I found my function, like when x equals 1.4, what is the y value? So let's see, minus ln 3 minus 1.4. Let's see what we get. Oops. So if we do minus ln 3 minus 1.4 would be 1.6, so minus ln of 1.6 plus 4 plus ln, that's not ln, plus ln of 2. So I'm saying that y is equal to 4.2. Can you guys see that? 4.2231. And you know what? It's not bad, is it? Like we basically approximated. We didn't know what the original function was. We just drew a tangent and stepped a little bit along the curve. Remember, all we're doing on this function is there's the point. We're trying to figure out that point over there. So what we did is we took a tangent. We stepped a little bit. Then we took a tangent again. And we stepped a little bit because we've done the process twice. And like we're not far off where we need to be, really. It's not a bad approximation. They might ask how do you make it more accurate, and you probably want to highlight this in your notes. Like, to improve the accuracy, Sometimes people say things like, "Oh, use more decimal places," and but no, that's like you're missing the whole point of the topic. To improve the accuracy, we use a smaller step. In other words, like if h was smaller, so if h was like 0.1, you'd only be going like a little bit along the curve, and as h gets smaller, the steps get smaller, and you end up being closer to the actual curve. All right, guys. Thank you.